Spectroscopic ellipsometry is a powerful optical technique for thin film analysis. It can provide optical properties such as refractive index, extinction coefficient, thickness, roughness, and others. It consists of analyzing the change of the polarization of light after being reflected off from the sample surface. From measuring the two parameters, psi and delta, one can obtain the desired optical properties of the sample. In the simplest case, the sample can be opaque, or, if transparent, it can be thick enough so that only the reflected light at the top surface is analyzed. In this simplest case, the refractive index and the extinction coefficient can be directly calculated by using this formula. This calculation is called the direct inversion of parameters. However, in the more general case, the sample is so thin that even being absorptive, the top and bottom light go through the detector. In such a case, the optical properties can only be achieved by means of computational methods, which require model definition and parameters variation in data fitting process. Data fitting is not easy, and in some cases can take months until it becomes reliable. It consists of 6 steps. First, a measurement is performed. Second, a computational model is designed, accounting the number of layers along with their respective thicknesses. For each layer, a mathematical description, such as Drude model for conductive materials, Lorentz model for dielectric absorptive materials, Tausch-Lorentz for amorphous materials, and so on. Third, an ellipsometric measurement is simulated from the designed model. Fourth, the simulated measurement is compared to the original one. The fifth step consists on a routine where the second, third, and fourth steps are repeated until the two data match. The sixth step consists of the calculation of the desired optical properties as long as the simulated data match the measured ones. The fitting process is strongly dependent on the thickness of each layer of the sample. Therefore, determination of the thickness is mandatory for faster fitting analysis. In this work, we obtained films of polyaniline whose thicknesses were responsible for the generation of interference pattern in the near-infrared region. This indicates that the material is transparent in such a range. The maxima in the measured data refer to constructive interferences. So, this allowed the analysis of the interference peaks with the aim of inferring the film thickness. This was done by specifying a small initial value of film thickness along with an initial guess for its refractive index with large uncertainty in the near-infrared region. Then, the film thickness is varied until reaching the condition of successive integer numbers for the interference order given by this formula. After reaching this condition, the uncertainty in the refractive index can be minimized guided by Sellmeier model. This procedure makes the determination of the film thickness more reliable. Once the film thickness is evaluated, the fitting process becomes easier. The focus now is on searching the best mathematical model that describes the optical properties of polyaniline. It turns out that the best mathematical model found is the one with 4 Tauch-Lorentz oscillators. In general, Tauch-Lorentz model is indicated to fit data from amorphous materials. The plot at the right side of this slide shows the comparison between the direct inversion of parameters and the optical properties calculated from the fitted model. It shows to be in agreement in the range where the sample is opaque, which suggests that the designed model here is reliable.